Good morning. So today we are going to discuss about DIF algorithm. We will revise the DIF algorithm and then we will start with discussion upon the comparison between DIF algorithm and DIT algorithm, right? So in the last lecture, we have discussed upon the strategy DIF algorithm. In that, what we have observed that input is in the sequential manner, whereas output is bit reversal. So as the output is bit reversal or the DFT values which are in the frequency domain, those values are being changed. And because of that, this algorithm is called as a decimation in frequency algorithm. So here is the algorithm or graphical representation of DIF FFT algorithm. So here you can observe that input x of which is in time domain, where it is x of 0, x of 1, 2, 3, 4, 5, 6, 7, which we have applied to the DIF algorithm. It is in the sequential manner. Input is in the sequential manner. So this is now what I'm representing is the stage number 1. So output now at the stage number 1, what we do, output is now divided into even point DFT and now odd point DFT. So in the even point DFT, which are x1 of 0, x1 of 1, 2 and 3. These are the even point DFTs. These even point DFTs have been calculated by performing addition operation. So here complex addition is taking place. This is a kind of butterfly structure. So here in the butterfly structure, we have seen that there are two complex addition and one complex multiplication that one need to apply. So here the even points have been calculated by using addition. This x of 0 gets added with x of 4 and first point is calculated. Then x of 1 will be added with x of 5, second point is being calculated. Third point takes x of 2 and x of 6. These 2 points are being added. So we will be obtaining next point DFT and last point DFT. So DFT computations, these are the even point DFT. Those are calculated by performing addition operation. Then next is these are the odd point DFT, and for odd point DFT you can observe here, it is clearly observed that these 2 points have been subtracted and then it is going to be multiplied by the Twiddle factor and output is being calculated. So first point is calculated, x of 0 minus x of 4 gets after subtraction it gets multiplied by Twiddle factor w raised to 0 suffix 8. Then next point is calculated, the next point that is being calculated where x of 1 minus x of 5, this subtraction is carried out and then this is being multiplied by the Twiddle factor w raised to 1 suffix 8 and second odd point is calculated. So for every odd point it gets multiplied by Twiddle factor, keep in mind that. So here these are the 4 odd points. So for 4 odd points, all the odd points gets multiplied by Twiddle factor. After performing subtraction, it is going to multiplied by the Twiddle factor. So again here this x of 2 minus x of 6, this operation is being performed and then it is going to multiplied by the Twiddle factor w raised to 2 suffix 8. And odd point is calculated. So x2 of 2 is the odd point, right? And the last point of this computation is x2 of 3, second sequence we are now talking about. So x2 of 3, last point is calculated by performing subtraction first. It is x of 3 minus x of 7 and after this it gets multiplied by w raised to 3 suffix 8. So this is the first stage of computation. So after every subtraction, it gets multiplied by Twiddle factor. Value of this first Twiddle factor is 1, w raised to 0, it is 1. W raised to 1, it is minus 0.707, minus 0.707, sorry, 0.707 minus J 0.707. So this is the value of twiddle factor which is going to get multiplied by the after subtraction. Then here in the next point of computation, this x of 2 minus x of 6 is carried out, and then it is going to multiplied by twiddle factor W raised to 2 suffix 8, and value of this is, if you calculate it, it is minus J. So this subtraction gets multiplied by minus J. And finally, this is the last point where it is going to multiplied by minus 0.707 minus J 0.707. So in this way, this subtraction is being carried out. 707 and output is calculated. So this is a stage 1 computation where 8-point DFT is now divided into 4-point DFT. This is n by 2-point DFT. So it is 4-point DFT where it calculates even point DFT. And second is, now here it is going to divide into a next 4-point DFT, because 8-point DFT is divided into n by 2-point DFT and next n by 2-point DFT. So this is going to be a 4-point DFT. This is going to be another 4-point DFT. Now in the next stage, what we are going to do? We are going to divide this 4-point DFT into further 2-point DFT, 2-point DFT. This odd point also we will be dividing this again further into 2-point DFT, 2-point DFT. So in this case, this is a even point DFT. Now again even point DFT, further it is going to divide into for even point and odd point. So how many stages we will be applying? We will be applying n is equal to 2 raised to L stages. Now here we have 8 point in our database. So what I'm going to say here, 8 is nothing but it is 2 raised to 3. So number of stages that one need to follow, L is representing number of stages. So one has to follow 3 stages in order to get the output. What we want to find? We want to get the output in terms of DFT values. So if I want to calculate DFT values, I have 8 points in my sequence. If I'm having 8 points in my sequence, I will have to apply 3 stages in order to get the output. If I'm having 4 points in my database at that time, what will happen? For 4-point computation, I will have to apply only 2 stages, 2 raised to 2. So if I'm having 4 points, I will have to apply only 2 stages. I have 8 points, I will have to apply 3 stages. If I'm having 16 points, I will have to apply 4 stages, right? So depending upon the number of samples or points which are present in the sequence, based on that we will have to apply number of stages in order to compute the final output or DFT values at the output side. So in the DIF algorithm, we are now here we have 8 points in the sequence, so we will have to apply 3 stages. So we have completed, we have done with the stage number 1. We have completed stage number 1. So we will be moving towards the stage number 2. Here in the stage number 1, the first half points, as I have told that these are the even points. So here those points have been represented. These are the even points and these are the odd points. These points have been represented here. Now this n by 2-point DFT, further we will be dividing into n by 4-point DFT, n by 4-point DFT. This is again n by 4-point DFT and n by 4-point DFT. And then finally it is going to divide into n by 8, n by 8 means only 1 point will be remaining at the end of this. So we'll see this algorithm in total. So as you know that this is the first stage of computation. After subtraction, here those odd points. These are the odd points. So these odd points gets multiplied by twiddle factor. So we'll see this. These are the twiddle factors. The points have been now multiplied by the twiddle factor. W raised to 0, W raised to 1 suffix 8, W raised to 2 suffix 8, W raised to 3 suffix 8. This is known as a stage number 1 computation. This is known as stage 1 computation. Yesterday we have solved the problem. Just I am taking the revision so that we can move further. Stage 1. This is the stage 2 computations. This is the stage 2 computation. Now n by 2 point DFT. Further it is divided into n by 4. So these are the even points and these are the odd points. Odd points gets multiplied by twiddle factor. W raised to 0 suffix 8, W raised to 2 suffix 8. So odd point gets multiplied by twiddle factor. Here again, from this odd values of DFT to odd points of the DFT, again this is divided into even and odd. So further odd points gets multiplied by twiddle factor, W raised to 0 and W raised to 2. And this is the last n by 8 point DFT. Only 1 point will be remaining here. This is being calculated by addition. This is being calculated by subtraction. As this is an odd point, this is even point, and this is odd point. So for odd point, again this is going to multiply by W raised to 0 suffix 8, W raised to 0 suffix 8. Here it is W raised to 0 suffix 8. So accordingly output is calculated, and output is in the bit reversal manner. DIF algorithm where the output is in the bit reversal manner. So x of 0, the next point that is being obtained is x of 4. Then here it is x of 2, x of 6, x of 1, 5, 3 and 7. So these are the output points that we will be getting at the output of this, right? So this is the entire algorithm, DIF algorithm. Okay, so now in the next we will see comparison between DIF and DIT algorithm. So this is some of the comparison point I have written here. The order of the sample. The first comparison point is order of the sample. So what we have observed in the DIT algorithm, input is in the bit reversed manner, whereas output is in the sequential order or in the natural order. Order will not be changing for the output in case of DIT algorithm, but input is the input is reordered. Input is represented in the bit reversed manner. So this is the first differentiation point between DIT and DIF. In the DIT algorithm, what we have observed that input is in the bit reversed manner, whereas output is in the natural order. The next point of comparison of DIT and DIF is we will talk about now about DIF algorithm. So what we have observed in the DIF algorithm, input is in the natural order or it is in the sequential manner, whereas output is in the bit reversed manner. So here input is in the natural order of the input will not be changed, but the order of the output is going to change. It is in the bit reversed manner. So this is the first comparison point between DIT and DIF algorithm. So this is important. Then next is both the computation we will be using butterfly operation or butterfly structure. But in the DIT algorithm, the multiplication is done before the addition. This is the DIT algorithm. What we do in the DIT algorithm, this is my butterfly structure. Let's say here I am performing this is, let's say, x of n point, and this is x of n plus n by 2 point. N plus n by 2 point. Before going for complex addition, these points are going to multiplied by Twiddle factor, and means here complex multiplication is taking first. In case of DIT algorithm, if you see the DIT algorithm properly, what are the observations? That we perform multiplication first. The complex multiplication is taking place first, and then addition is taking place, and subtractions are taking place. So 2 complex additions are required and 1 complex multiplication is required. But in case of DIT algorithm, complex multiplication is carried out first and then complex additions are performed. Whereas in case of DIF algorithm, in the earlier case only, we have observed in the DIF algorithm, the one supposed to perform addition and subtraction first, or the complex addition, and then multiplication by Twiddle factor is taking place. So let's say this is my x of n point. Let's say this is my x of n point, and this is x of n plus n by 2. So what exactly we do in case of DIF algorithm? In case of DIF algorithm, this complex addition is taking place, this complex subtraction, or we can say it as complex addition, doesn't matter. So these complex additions are taking place first, and then this is going to multiplied by Twiddle factor, w raised to n suffix capital N. So this is going to multiply by Twiddle factor after addition. After this complex addition, now what we do, we multiply the sequence by Twiddle factor, right? So here the multiplication is done after addition in case of DIF algorithm. In case of DIT algorithm, multiplication is done before the addition. That is the difference between DIF and DIT algorithm. And these are the vice versa. DIF is the transpose of DIT algorithm. These are the DIF is the transpose of DIT algorithm, right? So these two algorithms are complementary to each other. So DIF algorithm is the transpose of DIT algorithm. So these are the important points, which are the what we can say, these are the comparative points between DIT and DIF algorithm, right? I hope you all have understood this. So now these are the two structures. First is called as a DIT structure. The first structure is called as a DIT structure, and second structure is called as a DIF structure. So in the, if you see that both the structures, this is DIT structure and this is DIF structure. So we can say it as DIF structure is transpose of DIT structure. If we transpose it, it will be DIT structure, right? If DIT structure is transposed, then it will be DIF structure. If DIF structure is transposed, then it will be DIT structure. It is of transpose of each other, right? So now here the stages, this is this structure we have represented for n is equal to 8. So number of points present in the sequence are 8 points, and in order to find out DFT by using DIT algorithm and by using DIF algorithm. So if you observe that for each butterfly structure, now this is the first stage of computation. So for butterfly structure, first what we are doing, we are performing complex multiplication, and then complex additions are taking place and output is calculated. This is going to be a even points, and these are the odd points. So odd points are always gets multiplied by Twiddle factor. Odd points are always gets multiplied by Twiddle factor. That is very important thing. Here again 2 and 6. 6 is now acting as an odd point, therefore it gets multiplied by Twiddle factor w raised to 0 suffix 8, and then it is these 2 points have been calculated. First point is calculated by performing addition whereas second point is calculated by performing subtraction. In the similar manner, this for this 1 and 5, from 1 and 5, what you are observing that 5 is acting as a odd point, and this 5 gets added with x of 1, and this point is calculated. Similarly, this is going to be subtracted, and here the second point is calculated. So these even and odd points, by using this even and odd points, output is calculated. By using even and odd points, output is calculated. Now further in the, this is what is we are talking about stage 1. This is what we are talking about stage 1 in case of DIT algorithm. In that, this is the stage number 2 computation. These are the stage number 2 computation. In the stage number 2 computation, these 2 points are even point and these 2 points are odd points. So odd point gets multiplied by twiddle factor, w raised to 0 suffix 8, w raised to 2 suffix 8. Here again, these 2 points are even point and these two points are odd points. So even points, we don't do any multiplication, but the multiplication is being applied for odd point. So odd point gets multiplied by twiddle factor, w raised to 0 and w raised to 2. So this multiplication is being carried out. And now this is a stage 2 computation in case of DIT algorithm. Now further, this is the stage 3 computation. This one is the stage 3 computation, where in the stage 3 computation, these 4 points are even point and these 4 points are odd points. Odd point get multiplied by twiddle factor, w raised to 0, w raised to 1, w raised to 2 and w raised to 3. These are the odd points. So even point and odd point. Odd point gets multiplied by twiddle factor and output is calculated. And output is calculated. Okay, this the output is in the sequential manner. Here the output is in the sequential manner. So this is about DIT algorithm. And if we take transpose of DIT algorithm, we will be getting DIF algorithm. In the DIF algorithm, input is in the sequential manner. Input is in the sequential manner, and this output of this first stage, these 4 points are even point. Output of this second half part, the output is of odd point. These odd points gets multiplied again from even and odd point. Further, what we are going to get here, these 2 even points and these 2 odd points. In each and every stage, even points, we don't do any multiplication by twiddle factor, but we perform multiplication by twiddle factor if the sequence is odd. If the sequence is odd, what we do, we perform multiplication by twiddle factor. So here again, these are the 2 even points and these are the 2 odd points, and odd point gets multiplied by twiddle factor. Now in this kind of butterfly structure, what you are observing, this is a DIF structure. So we perform first addition operation and later multiplication is applied, right? First addition and second multiplication is applied. Whereas in the DIT algorithm, what are the observation? That the multiplication is performed first and then addition operation is being carried out, right? So that is the difference between DIT and DIF algorithm. This is the biggest difference between both DIT and DIF algorithm, right? So we will summarize the structure. Both DIT FFT and DIF FFT have identical computational complexity. For both the algorithm, computational complexity is exactly same, but the way of representation is varying. For n is equal to 2 raised to L, where L is the total number of stages, and at each stage has n by 2 butterfly computation. For each and every stage, n by 2 butterfly computations are applied. in each butterfly structure, in each butterfly computation, what we have observed, it requires 1 multiplication and 2 additions. For each butterfly computation, what we have observed, it requires 1 complex multiplication and 2 complex additions for each butterfly butterfly computation. Both DIT and FFT algorithm, DIT, FFT and DIF FFT algorithm, both have the characteristics of in-place computation. Both are having the characteristics of in-place computation. DIT FFT flow graph can be transposed to a DIF FFT algorithm graph and vice versa. I have told you, if I take transpose of DIT, I'm getting DIF. If I take transpose of DIF, I will be getting DIT algorithm. Both are vice versa to each other. Okay. So this is what we have. We were talking about DIF FFT algorithm. The one more thing that we will go through is Goertzel algorithm. We'll see this and then we'll stop the chapter number 4. I can say that it is completed, and then we will go with chapter number 5. So the last point of this chapter is Goertzel algorithm. This is in another way of computation of DFT. So one way of computation of DFT is by using DIT and DIF algorithm. The another way of computation of DFT is by using Goertzel algorithm. So Goertzel algorithm, this is specifically used, or the purpose of using this Goertzel algorithm is to find out FFT or is to apply or calculate DFT values. To calculate DFT values. The basic purpose of using Goertzel algorithm is to calculate the DFT values. We have used FFT algorithm for computation of DFT values only. Similarly, Goertzel algorithm is also we are going to apply for computation of DFT values only. So let us, we will have a look upon FFT algorithm, and then we will talk about why this Goertzel algorithm. We will talk about first FFT algorithm. So what you have observed that FFT algorithm takes n input data points or n data input data points from sequence x of n, and it calculates the n point DFT. Okay, so what we are talking about, the purpose of using Goertzel algorithm is to find out DFT values only. So we already studied about DFT computation via FFT algorithm, but now we will talk about FFT algorithm, and then we will go with why we should use Goertzel algorithm. We will understand the purpose of Goertzel algorithm. Okay, so in the FFT algorithm, what we have observed, both DIF and DIT, both the algorithm, it takes n point data sequence and compute n point DFT values. And while doing this, it requires the computation, the number of computation that is going to be required are The computations are n by 2 log of 2 n. These are the multiplications that are required, complex multiplication, and n into log of to the base 2 n. These are the complex additions are required. While performing n point input data sequence, it calculates n point output points or DFT values. While doing this, it takes n by 2. It takes n by 2 log to the base 2 n. These many complex multiplications, and n into log to the base 2 n. These many complex additions. So these are this is the computational complexity. Both DIT and DIF algorithm, for both the algorithm, computational complexity is similar. So how many computations are required? While talking about computations, we will talk about number of multiplications and number of additions. So number of multiplications, as I have told you, these are the number of multiplications are required, and these are the complex number of additions are required. But now we will talk about why to study about Goertzel algorithm. If we have such an efficient, fast calculating algorithm with us, which calculates the DFT values, why then we should use the this Goertzel algorithm? So in the Goertzel algorithm, why we are using? Because in some applications, selected DFT values is required to be calculated. We don't have to calculate the entire DFT values, only some selected DFT values that we want to calculate. So while doing this, we need not to follow these many multiplications or n by 2 log to the base 2 n. These many multiplication we need not to follow, whereas n into log to the base 2 n, these many complex additions also not required to be done. So in that case, for calculation of DFT values for selected only selected values of k, for selected DFT values I want to find out or I want to calculate, then doing so many multiplication is unnecessary task. So in order to avoid this, in order to find out a selected values of in order to calculate selected DFT values, instead of using DIF and DIT algorithm, here the algorithm developed called as a Goertzel algorithm. So this Goertzel algorithm is specifically used when you want to find out selected DFT values only. For that purpose, the algorithm is being used. This direct computation of DFT for selected values of frequency can be realized through linear filtering of X of n. So we are now we will be calculating the DFT values directly from this equation by using direct computations only. We will be calculating this by using direct computation only. Such a linear filtering computation of DFT can be implemented. Now this means here, if I want to find out X of 4 value only, in that case only that particular equation we can take, and this equation, from this equation we can directly find out that particular value only. We don't have to calculate the another value. This equation or this linear equation, we can, this linear filtering we can directly implement for getting particular DFT value only. So the definition of n point DFT, from this definition only we will be implementing. What we will do, we will be trying to implement the Goertzel algorithm. So we have the equation of DFT. What is that? X of k is equal to summation m varies from 0 to n minus 1 x of n w raised to k m suffix n. So this is the direct computation. This is the equation in order to find out DFT by using direct formula. So this is kind of direct computation. Now only some of the changes that we are going to do with this. and we will be implementing the Goertzel algorithm. So here multiply both right hand side and left hand side both by w raised to kn w raised to kn suffix n, because the value of w raised to minus kn suffix n, it is always equal to 1. This is always equal to 1. I will show you. W raised to kn suffix n, this value is always equal to 1. See, w raised to minus kn suffix n. This is nothing but, now I have the value of w suffix n. So what is that? E raised to minus j 2 pi upon n. 2 pi upon n multiplied by this is minus kn. So this n and this n cancelled out, minus minus will be plus, so it is simply e raised to j 2 pi k. So as it is multiplied by 2 pi, so what will happen? Whatever may be the value, integer value of k, it is e raised to j 2 pi k. So that is cos 2 pi k plus j sin 2 pi k. Sin 2 pi k is always equal to 0. So here we will be having only cos 2 pi k. So whatever may be the integer value of k, cos 2 pi k is always equal to 1, and therefore this value is always equal to 1. So what we have done, we have multiplied the right hand side by w raised to minus kn suffix n. Now from this twiddle factor, the exponential part, what we have done, we have taken k common. So if I take minus k common, so what will remain in the bracket? It is n minus m. So this equation I have rewritten. Summation m varies from 0 to n minus 1, x of n w raised to minus k suffix capital N into the bracket n minus m. So this is the equation 1. So here this is the linear time invariant system. We will be considering this as a linear time invariant system, in which this is going to be a input sequence and this is going to be a second impulse sequence. This is going to be a impulse sequence and this is going to be a linear sequence, and second sequence is shifted by some unit. So this by using this equation, now we will be implementing the equation. Now this is the second equation which I have considered as an impulse sequence. This is the input sequence and this will be considered as an impulse sequence. And here the system, we have assumed that this system is linear time invariant system. So this impulse response is represented here hk of n, which is represented as w raised to minus kn suffix n into x of n. So by the unit impulse response we have considered for this particular equation, right? So we will implement, as we have LTI system with us, so we can easily realize the system. So we will realize the system. So this system is having input sequence x of n. It's a unit sample response. Impulse response is w raised to minus kn suffix capital N into u of n. U of n is the unit step sequence, right? Here we have considered the sequence. This is my impulse, unit impulse sequence hk of n, which is w raised to minus kn suffix n into u of n. U of n is the unit step response. So this impulse response, we have the system. Now we have the system where input sequence which we are applying to the system is x of n. This is my unit sample response. hk of n is equal to w raised to minus kn suffix capital N into u of n. And here I will be getting output sequence yk of n. So we will be implementing the the system in a such a way that it will calculate only a selected value of DFT, selected values of K for input sequence X of n. K is representing a particular DFT value. So here K is fixed or it is a constant for the system. Now here we have implemented the system where entire input sequence is being applied, but only selected values of DFT is being calculated. K is fixed or constant for this system. The linear convolution of X of n and HK of n. HK of n is representing only the selected impulse response for only selected values of DFT. And when this linear convolution is applied between X of n and HK of n, the selected values of output sequence is obtained here. So this system, the entire system which we have represented here, it is shown Yk of n is equal to summation. Now this impulse is varying from minus infinity to plus infinity. X of n, HK of n minus m. This is the convolutional equation for the system which we have represented above, right? So HK of n, the value of HK of n, as you know that, what is the value of HK of n? HK of n is W raised to k n suffix capital N into U of n. So if I substitute the value HK of n minus m, only thing is it is being shifted by m unit. So it will be W raised to minus k. This is now n is replaced by n minus m, U of n minus m. From this equation, X of n, given that the value of m is exist between 0 to n minus 1. So this limit which we have taken from minus infinity to plus infinity, it will be only from 0 to n minus 1 X of m into W raised to minus k n minus m. So this equation, the equation from the above system which we have developed, it is exactly similar as we have obtained from the direct computation equation. So both the equations are same. Equation 1 and equation 3, both are same. So what we can say that by using linear convolution, we can implement implement a system where the system such that the system will compute the DFT for a selected values only. The system will calculate DFT for selected values only, and that is being now here written, or that is being represented by using Goertzel algorithm. So Goertzel algorithm specifically used for computing the specific values of DFT. Right. So this is the last part of the chapter. From next lecture, we will start with the next chapter, chapter number 5. So we have done with section 1. Section 1 consists of 4 chapters. Section 2 consists of remaining 4 chapters. So we will stop here for today's lecture.